Dear students, welcome to the lecture series on fundamentals of material science. And the first lecture is our introduction. So maybe a lot of you have already noticed that the human being civilization is characterized by the material that people use in certain period of history. For example, you must have heard the word Stone Age, Bronze Age, Iron Age, and Information Technology Age. And they are actually corresponding to different materials or the different mainstream materials that people used in that period of time. And for example, in the so-called Stone Age, the main material that people use is the ceramics. Okay, and here I just showed a few examples of ceramic tools fabricated by human beings in the Paleolithic, Mesolithic, and Neolithic ages. And the so-called Bronze Age is dated back between 3000 to 5000 before Christ. And the word or the term bronze is actually a copper-tin alloy, which means a combination of these two basic elements. And here shows some examples made by these copper-tin bronze alloys. And as a matter of fact, nowadays we already know the science behind the production of bronze. And this lies in the so-called phase diagram. Phase diagram of this alloy. The horizontal axis is the composition or the concentration of tin element in copper. Okay, so 20% here means you have 20% tin and 80% copper in this composition or in this combination. And the vertical axis is the temperature. So in each temperature and composition combination, you will have a certain crystal structure and certain property of your copper tin alloy. Okay? And even in Chinese very ancient classics, there are qualitative guidelines on how to make this copper tin alloy. For example, what is shown here, which is actually corresponding to this complex copper tin temperature composition phase diagram. And just for your information, which we will explain in more detail in the future, a phase means the regions with a uniform chemical composition and crystal structure. And then we enter into the so-called Iron Age. And essentially, the Iron Age, the material usually used is the steel, right? Which is an iron-carbon alloy, or a combination of iron and carbon elements. And here shows the earliest example of the iron sword in China, dated back a few thousand years ago. Probably the most spectacular steel or iron-based architecture is the Eiffel Tower, produced or manufactured over 100 years ago. And this makes a large amount of steels and a large amount of steel components and parts. And this is really spectacular structure that human being has ever made. And usually a nation's economy can be measured by the total volume of steel it can produce. For example, this shows the GDP of China together with the steel output. Okay, so you can see that there is an increasing number of steel production with the increasing total GDP of the country. So they are really, so the amount of steel the country can produce is a really measure of the strength of economy in that country. And essentially, the science behind steels is on this phase diagram, or in particular is on this iron-carbon phase diagram, where in different, again, so it looks very complex. So in different regions with this iron-carbon composition at different temperatures, you can have different material structures and you can have different material properties. For example, you may have a low carbon steel, high carbon steel, and you can have this so-called pig iron with different properties. And they are always used in our daily life. Okay, And then from the 1950s, we enter into this so-called information technology age. And the basic material is the semiconductor, or essentially it is based on silicon semiconductor. And this is a complex view of your circuit, your actual circuit, and each of this chip is cut from this silicon wafer, okay? And silicon have fairly complex structure like this. So it's so-called a diamond cubic structure, which I will explain in our future lectures on crystal structure. So because it has a certain crystal structure and a certain electronic structure especially, it can have very controllable properties that are favorable for the electronic applications. And with modern technology for production, and you can fabricate these very complex structure of transistors, and these transistors makes your chips. And as I said, the science or the unique properties of silicon semiconductor for the information technology is lying in a certain electronic structure, or in particular it is called electron band structure, where you can really control how electrons interact with external stimuli, and the density of electrons can be easily controlled in semiconductor silicon. And we will also see a little bit of this when we talk about point defects in our future chapters. So now we move on to the topic of material division, or the different types of materials. They can be divided into different groups based on their chemical composition, properties, or crystallinity. And the chemical composition, you can easily imagine that you may have metals, ceramics, polymers, or composites. And this is a very good example. So for the same liquid of Coca-Cola, you can have different material for the container, right? You may have a glass container, right? And you may have aluminum cans, which is essentially a metal. Glass container is essentially a ceramic. And you can also have a polymer-based plastic bottle for your Coke, right? The second way to divide different materials is by their different properties, okay? So you may have this structural, so-called structural material, where under the force field, you are mostly consider their response under this force field, and they are used for the so-called structural applications. And as comparison to this structural materials, you may also have this functional material, where you consider, instead of the mechanical properties, you consider this acoustic, thermal, optics, magnetic, all kinds of functional properties. And materials can be also divided into different groups based on their crystallinity, or the crystal structure. And you have single crystals, where you have a complete translational symmetry and periodic arrangement of items across the entire material. That's called single crystal. And polycrystal is made up of a number of single crystals, and these single crystals in the polycrystalline material is divided and separated by a defect called grain boundaries. And then if the crystal, or if the material doesn't have a crystal structure, or doesn't have this so-called translational symmetry, then the material is called amorphous material. There's no long-range order and translational symmetry, okay? And a more recent concept, or a more recent subgroup of material, is the so-called quasi-crystals, which actually won a Israeli scientist a Nobel Prize a few years ago. Okay, so that's somewhere between your amorphous material and your single crystal. Okay, so how to choose materials? So materials have a lot of properties, and for a particular application, you really need to consider the combination or the comprehensive properties, a lot of properties. For example, for a particular application, you may need to consider the chemical properties. For example, its composition, its structure, its corrosion resistance, and you also need to consider the physical properties, for example, color, density, melting point, and things like that. And you may also need to consider its mechanical properties, for example, how strong the material is, how ductile the material is, and you also need to consider the dimension, so how big you can make this particular material. So in this class or in this lecture on material science, we are mainly focused on the so-called tetragonal material science, how to correlate the structure, processing, performance, and properties of a material. So hopefully after this lecture or this series of lectures, you will be able to at least qualitatively know how to process a material and to make the material into a particular structure or a proper structure, so that this proper structure can be made to have certain properties. And the certain properties of the materials, when they are made into certain parts or components of your system, will have certain desired performances of your designer, right? So essentially, the topics in this lecture series will include atomic bonding and crystal structure, defects in crystals, mechanical properties, recovery and recrystallization, diffusion, phase diagram, and phase transformation. Okay, the basic textbook is this English textbook called Fundamentals of Material Science and Engineering, and the Chinese textbook or the Chinese reference book is this one published by Shanghai Jiao Tong University. So we have several primary reference books and on different topics, and along with the lectures, I will give the citations of these reference books properly. Okay, so today's lecture we focus on the introduction of fundamentals of material science. Thank you very much.